in the next 1.5 hour, we will be having a discussion on basics of remote sensing. So, in this context, if we need to collect any kind of scientific data, we have two options with us. One is collection of the data in situ, that means go to the site itself, collect the samples, analyze it, and interpret the results. This is one method of collection of information which is scientific. This is also called field data collection. The another option with us is remote sensing. That means you are collecting the information by not going to the site itself but from a remote location. So, in this context, we will be discussing the second option with us, which is remote sensing, and we will first try to answer the basic three questions of science, which is what, why, and how. So, coming to what is remote sensing, it is both science as well as an art of obtaining information about three things. The three things can be an object, let's say a building of interest, an area, let us say a city, or a phenomena, for example, rainfall or cloudburst, etc. Now, to get the information about these three things, we require the analysis of the data acquired by a device which is not in physical contact with the same. It is science because this sensing is involving scientific principles and we build technology to do that. It is art because the remote sensing interpretation depends upon the skill of the interpreter. So, collectively, it is both science and art. In fact, it started as an art. Right, so once we have understood what is remote sensing, why should we go about it? We have seen the first option with us was field measurements, which is basically more accurate and can give you a real picture or the ground picture of the site. Whereas the second option is remote sensing, which is having its own limitations. Then still we are going to discuss this subject in the next 1 hour, or you will be discussing further topics in continuation. That means there are some advantages of remote sensing over field-based measurements. The very first is systematic data collection. So if I ask you to collect the samples from the ground, let's say 10 or 20 people go to the ground, take the samples, analyze and interpret. Now, this procedure might involve human errors. It may also involve the differences in the sampling. So, the overall information can become subjective depending upon how the samples have been collected. Whereas remote sensing enables, it gives you an option to have a systematic data collection, which is, let's say if it is a scanner, so it's going in a particular fashion, click, 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 and you collect the data in a systematic pattern. The objectivity comes into the data collection. The second very important advantage with remote sensing is it enables the three-dimension information of real objects. All of us are using Google Earth these days, and you can see the data coming from stereo satellites is giving us the spectacular pictures of 3 dimensions of real objects. Then another advantage with remote sensing is repeatability in both space as well as time. So we can revisit a particular area after a particular interval of time, depending upon which type of satellites or platforms we are using. So same area can be covered in different points of time, which is repeatability. Then comes a very important advantage, which is global coverage. For several applications, we require the data at a global scale as a whole. So that is also supported by remote sensing. The only solution sometimes for the otherwise inaccessible areas, for example, let's say there is a disaster in some region. Now, in order to collect the information, we can't be risking lives to collect field measurements, right? So in that case, remote sensing becomes the only possible solution. There are a lot of other advantages also associated with remote sensing, but by and large, it gives you a multi purpose information. That means the same data which is collected by your satellite or by aerial platforms or by UAVs, etc., that can be interpreted or analyzed in a differential manner by, let's say, a person of agriculture, or from forestry, or from photogrammetry, or from marine science, or from atmospheric science, etc. Right? So, same information, but it can have multiple purposes. However, it is not everything. That means we cannot do away with the field measurements. In order to calibrate the instruments before sending them on board, it has to be first calibrated with respect to the ground targets or field measurements. So, for calibration, as well as once the data is achieved by a remote sensing instrument, it has to be analyzed and it has to be assessed for its accuracy with respect to field measurements. The field measurements are also called ground truth because that's the best possible measurement of any phenomena that you can have. So, the measurements or the analysis by remote sensing has to be validated with respect to the field measurements. So, both for calibration as well as for validation, we are still dependent on field measurements. Plus, some topics of research are better addressed by using field measurements. For example, for subsurface analysis, up to a certain extent, remote sensing is helpful, but beyond that, we are still dependent on ground measurements. So, as long as remote sensing survives, the field measurements have to survive. Now, when we understand that there are several advantages of remote sensing over field measurements, let us see how to have this process happen. So, to enable remote sensing process, we need to have certain components to realize it. So, the very first component is the source of electromagnetic radiation. So, it can be natural source or it can be a source on the platform itself. So, it has to be a source of electromagnetic energy. Now, this source illuminates your target, the target that whose properties you want to assess or analyze. So, you need to have a target, you need to have a source of light that illuminates the target. Now, the target, depending upon its properties, will be reflecting or it will be absorbing and then re-emitting, or if it is having some transparency, it will be transmitting the radiation. Now, let's say one of these components reaches your sensor. The sensor here has to be a combination of your detector, that is your camera or any sensor, plus the platform that can carry that sensor. So, sensor alone won't be able to function. It has to be supported by a proper platform. This platform can be space-based, it can be airborne, it can be ground-based also. So, you need to have a sensor mounted on a platform. After that, once the data is collected by the sensor on board, it has to be transmitted to the ground receiving station. So, for let's say this picture or this cartoon depicts the example of a space-based measurement. In that case, whenever your ground receiving station or the antennas here come in line of sight, that's called locking. Whenever this comes in line of sight of the satellite, that time the data will be transmitted to the ground receiving terminal. In India, we have this at Shadnagar. Now, once the data is collected here at ground receiving station, it has to be pre-processed. What does pre-processing mean here? Means we free the data from some known errors. Okay, this can be geometric correction, this can be radiometric correction, or it can be just the conversion of the data into a usable format by the user. So, some pre-processing, some level of pre-processing is done here. and you can get different levels of products. The raw data usually comes as level 0, then some sort of corrections applied to it comes as level 1, followed by level 2 with some further processing applied to it. Let's say it can be a product, and level 3 is generally gridded products, right? So different levels of products are available. For each satellite, you can browse through what are the levels defined by the satellite providers. It can vary from one satellite to another. Then once the data is converted to a usable format, here it is given to different applications or the users. Another point to notice here is for Earth based observations, there is also an atmosphere that covers the Earth, and the signals, both while incoming from the source to the target as well as from target to the sensor, encounters this interaction with the atmosphere. Okay, so this may be wanted, this may be unwanted. Unwanted when we are looking at the Earth's surface targets. Wanted when we are looking at specific properties of atmosphere. So for atmospheric based remote sensing, we are concerned with these interactions, and for Earth surface based interactions, we would like to remove this noise from the signal. Whatever alterations atmosphere has done to the signal, that part we would like to correct for. So that's where atmospheric correction comes in. So as a whole, what we have is we have to have a source of light, we have to have a target, we need to have a sensor plus a platform, we need to have a ground receiving station, we also need to pre-process the data, and then we can use it for our applications. This example showed here that light, a streak of light is falling on the target, part of it is getting reflected and is going to the sensor. So this type of sensing where the source of light is not on the platform itself, for example sun here, it's called passive remote sensing. Also in this case, because we are observing the reflections from the target, this is also known as reflective remote sensing. Another way of remote sensing could be this dotted blue line. You can see here it is a dotted line but with double arrows. That means the platform is carrying a source on board. So the source on the platform illuminates the target. That means you can control the illumination. You can control the source of light both during day as well as night. So night and daytime remote sensing is possible with this. And you can receive the backscatter signal and record it. So this type of remote sensing where the source of light or the source of illumination is used, which is carried on board, is called active remote sensing. Right. There is another form of remote sensing. You can see this where the light is coming from the target. There is no incoming light arrow, right? So this is an example of emissive remote sensing. See, all the objects on which are above 0 Kelvin are emitting some source of some amount of radiation. For Earth, this radiation falls maximum in the thermal regime of electromagnetic spectrum. So that's why this emissive remote sensing sometimes is also called thermal remote sensing. Here you can see that the target itself becomes the source, right? Because we are also a source of energy. We are also emitting some form of energy. If the sensor is able to capture that form of energy, then it is called emissive remote sensing. But it is also passive remote sensing because we are not using any source on board. So these red lines are examples of passive remote sensing, and this blue dotted line with double arrow is an illustration of active remote sensing. So with this, we also get a purview of what kinds of remote sensing are possible. In the following class, maybe tomorrow or day after, you will also come across in detail how active remote sensing is different from passive remote sensing, which one is costlier, what are the pros and cons, etc. But in today's class, you just try to understand that based on what we are sensing and how we are sensing, we have different categories of remote sensing. We have reflective remote sensing, we have emissive remote sensing, there is passive remote sensing and active remote sensing here. Right. So once we have understood the three basic questions, that is what, why, and how, next let's try to see what will be the next focus of today's class. We will try to learn the properties of electromagnetic radiation, because it is the electromagnetic radiation or energy that we are going to sense. So we need to understand its properties. We also need to understand how the electromagnetic radiation interacts with the target as well as the atmosphere. The rest part of it, like platforms and sensors and data reception on the ground or data pre-processing, will be followed or covered in the subsequent classes. But for today, let's try to understand how the electromagnetic radiation interacts with matter. Okay, so to understand that, first let's see some basic understanding of electromagnetic radiation. There are two theories in physics. One is wave theory and another is particle theory. Wave theory considers that electromagnetic energy is in the form of continuous harmonic sinusoidal waves. These waves are of oscillating electric fields and oscillating magnetic fields. So oscillating electric fields and magnetic fields, both perpendicular to each other, right? So if this is the electric field and this is the magnetic field, so the energy propagation will be in the perpendicular direction to these two directions, right? So electric and magnetic oscillating fields at each point in space and time, and energy is propagating in the perpendicular direction. This is the wave theory. The another theory is particle theory, which considers that electromagnetic energy consists of discrete units, which is called quantum. Okay, for light particularly, it is called photon. Both the theories are just opposite to each other, but light exists both as particle as well as wave. Let's see some basics of wave theory. So electromagnetic wave, as I just discussed, this is a transverse wave. Transverse, why? Because the propagation of energy is in perpendicular direction to the oscillations of electric and magnetic fields, right? Then there is something called crest, which is the topmost point on the wave. This wave can be of electric field or of magnetic field. One of them is shown here. That means the other is also there at the background. So trough is the lowest point of the wave. Wavelength is the distance between two identical points on the wave. Frequency is the number of cycles per second, right? So the number of wavelengths that pass a point in a set period of time. So these are some basic terms, and the frequency and wavelength are inversely related. Longer is the wavelength, smaller is the frequency associated with that wave, right? So, and this is connected using a constant, which is the speed of light. C, this is the speed of light, 3 into 10 to the power 8 meters per second. C is equal to lambda, that means the wavelength times the frequency, that is nu. Then the energy of a photon is given by h nu. H is the Planck's constant and nu is the frequency. So these are some terms which are related to electromagnetic waves. It's an interesting equation, which is also called wave particle duality. So one theory says that light exists in the form of waves, another theory says it exists in the form of particles, but actual existence of light till date we could not separate both the behaviors, and light exists both as particle as well as waves, right? It's just that we are tapping one nature to study some properties and the other for the other properties. So there is an equation which is very interesting. This is a hypothesis proposed by de Broglie. What it says is the momentum of photon is inversely proportional to its wavelength. Here wavelength is also called de Broglie wavelength. You see that momentum is a property of a particle, right? So momentum is mass into velocity. So photon usually you're using have the photons having zero mass, so momentum should be zero, but there is a finite momentum which is explainable by this equation, where momentum is inversely proportional to wavelength and equated using the Planck's constant. So this duality or this equation embodies in itself the wave nature of light in terms of wavelength and the particle nature of light in terms of momentum, both connected at one place. Right. So this is an electromagnetic spectrum illustration. You can see that if you put on, there are different components of electromagnetic radiation. We have categorized them based on their wavelengths, or you can say frequency or energy, because these are all connected. So if you see from here, cosmic rays going to gamma rays, then to X-rays, then ultraviolet, visible, IR, microwaves and radio waves, you can see that the wavelength is increasing from 10 to the power minus 18 meters and going up to 10 to the power 2 meters. And associated frequency, if you see, the highest frequencies are borne by cosmic rays and the lowest by radio waves. So corresponding highest energies by cosmic rays and the lowest by radio waves. For Earth-based observation studies, we are restricting ourselves to this range, right? So ultraviolet, visible, infrared and microwaves. Ultraviolet is mainly used for atmospheric studies. Visible, IR and microwaves, both for atmosphere as well as for land surfaces of Earth. Then coming to visible range, extends from 0.4 to 0.7 micrometers. Infrared range ranging from 0.7 to 3 micrometers, and from 3 to 100 micrometers. 0.7 to 3 micrometers is the range of reflected IR. So here the remote sensing that takes place uses the reflective principles. So its sensing is similar to that of visible light. In fact, together with visible light and the reflected portion of IR, that means 0.4 to 0.7, and from 0.7 to 3 micrometers, this entire range is also called optical range of remote sensing. And from 3 to 100 micrometers, it is the thermal IR. We do not use the entire range, we use a portion of it depending on where is the Earth emitting maximum, but its entire range from 3 to 100 micrometers is called thermal IR. Coming to microwave range, it's usually expressed in the form of frequency bands, P band, L band, S band, C band, etc. This will be covered later in detail in the microwave classes. Here, it is important to mention here that microwave attained its popularity because of its ability to penetrate below the clouds also and bring in the signals from the surface. But now it's being used in almost all the applications. Now, once we understand that we are going to measure the radiation, now how do we measure this radiation, right? There is a measurement of radiation in some terms. So let's see those terms here. Before we go further, let's see a solid angle concept. So as we have an angle in 2 dimensions, similarly we have an angle in 3 dimensions. So in 2 dimensions, the angle is defined as the length of the arc subtended on the circle divided by the radius. This is how you define an angle on the surface of a circle from the center. But when in 3 dimensions, this circle becomes a sphere and this arc will become a circle on the sphere. So the solid angle is also defined as the surface area of that circle on the surface of the sphere divided by the square of the radius. So this is solid angle and its units are in st-radian. Okay, st means solid, 3D, and radian is the unit of angle. So in 3 dimensions, the angle which is solid angle is defined in st-radian. This These are some terms associated with radiometry. The basic unit of measurement of radiation is energy. If you add the information of time to it, that means energy per unit time, you get radiant flux. If you further add the information of area to it, that means rate of change of radiant flux with respect to surface area. Actually, these are all the differentials. So, differential of energy with respect to time, or differential of flux with respect to surface area, like that. So, that becomes flux density. Now, depending upon whether the light is incoming or it is outgoing, we have two terminologies. For incoming light, flux density is called irradiance. For outgoing light, this is called excitance. And for a point source, we are not concerned about the surface area, rather we talk in terms of intensity. So energy, the radiant flux per unit solid angle is called radiant intensity. This is mostly used for point sources. And then comes the radiance, which is the flux density per unit solid angle per unit projected surface area. Right, so the flux density per unit solid angle, or you can move from this direction also, that is intensity per unit projected surface area. So this becomes radiance. This is the quantity that we generally measure using the using the sensors. So the energy which is falling on the ground from coming from the sun is usually measured in terms of irradiance, and the energy which is measured at the sensor level is in terms of radiance. All these terms can be measured spectrally, so all these terms can also be called spectrally, like spectral radiance, spectral flux density, spectral power. Why spectral? Because your sensor will be limited to certain range of wavelengths. According to that range, you will measure the energy. Right, so then coming to black body. Black bodies are some idealized objects which absorb and re-emit the radiation in a characteristic continuous spectrum. Okay, this spectrum is dependent on the temperature. Okay, so this radiation is called black body radiation. This is not the emitted radiations are not from a real object. This is an hypothetical idealized object, right? But some real objects may behave close to that of black body in certain situations. We will see them how. So this is how a black body spectrum looks like. On the x-axis you have wavelength, and on the y-axis you have spectral radiant excitance. That means the excitance, the quantity which we just saw for flux density, light coming out from the source. So it is spectral because it is measured in certain spectral range. So you see that if you focus on one of the curves, let's say this curve here, you see that as the wavelength increases, the spectral radiant excitance increases, reaches a maximum here, and then starts falling down. I'm sorry. And so this wavelength at which there is a peak emission from the source, this wavelength is called peak emission wavelength, or wavelength of peak emissivity. Okay, and below this wavelength, if you see here, the behavior is as you increase the wavelength, the excitance is increasing, but after that the excitance falls down, but it never touches the x-axis whatsoever. That means there is a finite amount of energy at all the wavelengths from a black body, and this behavior is shown at a particular temperature, at a fixed temperature. And if you see that while you increase the temperature, the curves keep on rising. These are not crossing each other anywhere. That means at all the wavelengths, the excitance keeps on increasing, building up. So if you keep on heating a black body, the overall excitance from the black body keeps on increasing, irrespective of the wavelengths. For all wavelengths it's increasing, but you see that the peak is shifting towards a lower wavelength. That means the wavelength of peak emission, it starts decreasing as you increase the temperature. It is, for example, let's say if you have an iron rod, if you heat it first it will become red hot, then further you heat it, it will become yellowish. So the wavelength keeps on shifting. Though iron rod is not a black body, but sometimes certain objects behave close to that of black body. Right, so from Planck's law of radiation, there are two corollaries. If you integrate the Planck's law, that means you will get the overall area under the curve. That means total excitance in the entire spectrum you will get if you integrate the Planck's law. And this gives you the information that total excitance is directly proportional to fourth power of temperature. This law is known as Stefan-Boltzmann law. While if you differentiate the Planck's law, you will see that the peak wavelength, the wavelength of peak emission shifts towards lower side as you increase the temperature. So this wavelength of peak emissivity is inversely proportional to temperature. This behavior is called Wien's displacement law. These are nothing but coming out from the Planck's law itself. Then why do we study black body at all? It's a hypothesized ideal object, but real objects in certain situations behave close to that of black body. In those cases, you can model the real object as close to the black body as its behavior is. So, how close a real object behaves with respect to a black body is given by a figure of merit. This figure of merit is called spectral emissivity. So, spectral emissivity is the efficiency with which the real materials emit the thermal radiation at different wavelengths. As I said, it is a figure of merit. That means it is a ratio. So, the ratio the spectral emissivity is given by the ratio of spectral excitance of a material, real object, which exists in nature, divided by the spectral emissivity of a black body at the same temperature as that of real body. Okay, so spectral excitance of a real object divided by spectral excitance of a black body at a constant temperature. This quantity is known as spectral emissivity. Now, because it is normalized with respect to spectral emissivity of black body, its maximum value will be 1. And because it is the spectral excitance, that means the energy coming out from a source or from a target, whatever, the minimum value can be 0. So, the spectral emissivity varies between 0 and 1. For black body, the real object is the black body itself. The figure of merit is 1 at all the wavelengths. There is something called a gray body also. We define it in such a manner that its behavior is same as that of black body, but emissivity is less than 1. Okay, that means the spectral emissivity is independent of wavelength. We call it spectral emissivity, but it is independent of wavelength. For all wavelengths, the value is same, less than 1. For perfect reflector means those objects which reflect every energy that falls on them. That means nothing is absorbed, so nothing is re-emitted. So spectral emissivity is 0. All other real objects, this spectral emissivity will be varying somewhere between 0 and 1, but it's a function of wavelength. Now coming to, as I said, this was all about the electromagnetic radiation, the source of electromagnetic radiation, the laws of electromagnetic radiation. Now coming to how the electromagnetic radiation interacts with matter. At this point, we'll take a 2 minutes break and we'll be back. All right, so welcome back. Now let's continue with the electromagnetic interaction with matter. So there are two types of interactions possible. One, interaction at the boundary of two surfaces. So at the boundary of two media. So there is medium 1, there is medium 2, and there is a boundary creating the separation between the two mediums. So here when the light comes, it will either have a reflection or it will have refraction. But within a particular medium, same single medium, light comes and interacts with the particle. It can, part of it can be absorbed and part of it can be scattered. Scattered means it can be redirected in different directions. So we have these two scenarios with us. Either the electromagnetic radiation is going to interact at the boundary of two media or within a single medium. So coming to the interaction of electromagnetic radiation with the Earth's surface, here the light which is incoming is composed of two signals. One, it gets reflected, another it gets transmitted, and part of it which is traveling inside can be absorbed by the medium. Now this absorbed energy can be re-emitted by the target depending upon its emissivity, and that means temperature and wavelength. So here in case of optical remote sensing, that means we are talking of reflections from the object, we are concerned with the reflected energy. In case of thermal remote sensing, we are concerned with the absorbed energy because it is a function of absorbed energy which will be re-emitted. No object is a perfect source or sink of energy. So whatever energy we are absorbing, we will be re-emitting also depending on our spectral emissivity. So for having the thermal remote sensing, you should be concerned about the absorbed energy. So for optical remote sensing, we are concerned with the reflected energy. So let's take the case of reflected energy. Thermal remote sensing, you can have a separate discussion with a scheduled syllabus. Now for the reflected energy, we are concerned with the reflective properties of the target, right? So there can be two types of scenarios. One where the surface is smooth, that means mirror like, so you will have a specular reflection. Angle of reflection will be equal to the angle of incidence. Whereas if the surface is rough like this, your incident light can be in one direction, but the reflected light can be in multiple directions. It can be evenly spread in all the directions, or it may be having more directionality in some particular direction depending upon what kind of surface you have. As an example, for optical remote sensing, if you have a smooth road, the surface here may behave as specular reflector. Whereas if you look at a tree canopy, because the leaves are oriented in different directions, so the light, if it is coming in one direction, may be reflected in different directions just because the orientation of leaves is different. So your targets can be smooth targets, or it can be rough target. Your surface can be smooth surface or can be a rough surface. But how to tell whether the surface is rough or smooth? So here is a criteria which is called Rayleigh criteria that tells you if h is greater than lambda by 8 cos theta, where h is the average undulation of the surface. See, every surface will have some form of undulation. If it is having some friction, there is some undulation in the surface. Now it can be questionable whether the undulations are in microscopic level or at nanoscale, or it is in centimeter level, or it is in meters level, depending on which type of surface we have. So if you have an average undulation of the surface and you can measure it, that is roughly taken as h. Actually it is the root mean square height variation above a reference plane, but for simplicity just take it as average undulation of the surface. And we have on the other side, lambda by 8 cos theta is a factor, where lambda is the wavelength in which you are observing the surface and theta is the angle of incidence. So if h becomes greater than this factor, the surface appears rough on a remote sensing image, whereas if the reverse happens, the surface appears smooth. Okay, so there is a question you can try on your own. If the surface is the same, h is the average undulation, let's say its undulation is 1 micrometer, and if I have two types of wavelengths, one is lambda a which is 80 micrometer, another is lambda b which is 80 nanometer. If you try out this, checking this criteria, you will find maybe the surface changes its behavior from rough to smooth or from smooth to rough in going from one wavelength to another wavelength. So whether to say a surface is rough or smooth also depends upon which wavelength we are looking at and what is the angle of incidence. Right. The next important subject is spectral signatures. I guess there is a complete 1 or 1.5 hour dedicated in the following classes to you. But here, for the time being, let's understand the concept itself. Spectral signatures are the unique identification of each feature. So, signatures mean something which is your identification and it has to be unique. So the spectral signature of, let's say here, vegetation is different from that of soil. Okay, the spectral signature of dry soil will be different from that of wet soil. The spectral signature of dry soil or sand and dry silt will be different, right? So you understand the concept that each feature in different stages also have a different spectral signature. You can identify them based on their spectral behavior. In optical remote sensing, these signatures are defined in terms of spectral reflectance. So that means on the x-axis you have wavelength and on the y-axis you have spectral reflectance. And the different features will exhibit different characteristics here. Right, as I said, the details will be covered in the forthcoming class, so I'll refrain from discussing much on this, but here you just try to understand that signatures of different material is different. The signature of forest will be different from agriculture. The signature of rice will be different from that of wheat. The signature of basmati will be different from non-basmati. The signature of basmati A will be different from basmati B. The signature of diseased basmati A will be different from healthy basmati A. You understand, there are variations to the health of the vegetation that also is covered in their spectral signatures. So knowing the spectral signature means you know the material. Next, coming to the interaction of electromagnetic radiation with atmosphere. First, Earth observation, we can't do away with this part, whether or not we like it or not. For if we are looking at, as I discussed in the very beginning, if we are looking at the atmosphere itself, you will be decoding this interaction. You will want this interaction so that you can get the information about the atmosphere. For Earth surface remote sensing, that means let's say you want to take a picture of Earth's surface. That times atmosphere behaves the atmosphere alters the signal both while incoming as well as outgoing. So it behaves as noise. This noise can manifest itself in terms of absorption and scattering. With absorption by atmosphere, we are limited to atmospheric windows. What are atmospheric windows? These are those spectral regions where the electromagnetic radiation is passed through without much attenuation. That means the atmosphere becomes transparent to these electromagnetic radiation. If you look at this x-axis, you have wavelength, and on the y-axis you have percentage of transmission. You can see that this transmission is high at certain range of wavelengths. Then there are some dips here, here, then again there is a rise, peak, and then there is a dip. Wherever there is a peak, that means the atmosphere is allowing the passage of these electromagnetic radiation. Okay, so these regions of electromagnetic radiation are atmospheric windows. So if my interest is to look at the Earth's surface, I'll be creating the sensors in these range wherever you have a peak. But wherever you have a dip, this is a broad dip, let's say. If my purpose is to study the Earth targets, the Earth's surface, I cannot be creating a sensor here in this region. right? So I am left only with the atmospheric windows. Whereas if the purpose of my study is to, let's say, understand the water vapor or carbon dioxide, then I'll be interested to have a sensor in this range, because the greater dip in this channel means the greater amount of that particular gas or constituent of the atmosphere, right? So depending upon what is my purpose or what is the application, I'll be looking at different channels. And also, absorption by the atmosphere limits the signal both while incoming as well as while outgoing. So it diminishes or it lowers down the signal overall. So the effect of absorption on remote sensing is we are left with atmospheric windows to observe the Earth's surface, and the signal is lowered down, it is diminished. The other process, which is scattering, that means the redirection of light, depends upon the wavelength which is interacting and the size of the scatterer. There are other properties like chemical structure of the scatterer, its physical properties, etc. But by and large, these two quantities, that means the wavelength of interaction and the size of the scatterer, decides what kind of scattering it is. I am restricting myself here to elastic scattering. That means the wavelength of outgoing radiation is same as that of incoming radiation. So in elastic scattering, there are three forms: Rayleigh, Mie, and non-selective. If you go to inelastic scattering, that means the wavelength of scattered light is different, may be different from that of the incoming light. That becomes inelastic scattering. Raman scattering is one such form. So here I am restricting my discussion to elastic scattering. That means Rayleigh, Mie, and non-selective scattering. So for Rayleigh scattering, what happens is the amount of forward scattering is equal to the amount of backward scattering. For Mie scattering, the amount of forward scattering is more compared to the backward scattering. These two types of scattering, Rayleigh and Mie, are also called selective scattering. Why selective? Because their behavior depends upon the wavelength of light which is interacting. And larger is the wavelength, smaller is this type of selective scattering. For Rayleigh, this dependency is lambda to the power minus 4, and for Mie, it is roughly lambda to the power minus 2, but it can vary between lambda to the power 0 to lambda to the power minus 4. These two are dependent on wavelengths. So the scattering cross section is dependent on the wavelength of light which is interacting. If you have blue and red wavelengths, blue will be scattered more in Rayleigh as well as in Mie. But in Rayleigh, blue will be much scattered compared to whatever it is scattered in Mie. In non-selective, whatever wavelength is coming, it is equally scattered. So here, if it is blue or it is red, both are equally scattered. So this type of scattering, Rayleigh scattering, is shown by very, very small particles. When the size of the scatterer is much smaller compared to the wavelength of light which is interacting, it's called Rayleigh scattering. When the size of the scatterer is comparable to that of wavelength of light which is interacting, it becomes in the range of Mie scattering. And when the size of the scatterer is much larger compared to the wavelength of interaction, then it is falling in the range of non-selective scattering. Rayleigh scattering is exhibited by gaseous molecules in the atmosphere. Mie scattering is experienced by smoke, is shown by smoke and haze particles, that basically aerosols. And non-selective scattering is exhibited by bigger particles like cloud droplets. But the effect of scattering on remote sensing is it can modify the spatial as well as spectral distribution of incoming and outgoing radiation. More is the amount of scattering at a particular place, more will be the haziness in the image. So contrast will reduce, right? So scattering will reduce the overall image quality, right? So this is the effect of atmosphere on remote sensing. In this last 1 hour, we try to learn the overview of remote sensing. I'll just wind it up. We have learned about what, why, and how to carry out the remote sensing process. Then we learned about what we are measuring. We are measuring the electromagnetic radiation. So we need to understand its properties, some terms, some definitions, wave particle duality, laws of radiation, spectral emissivity, etc. Then we also discussed the interaction between electromagnetic radiation and matter. This matter can be target or atmosphere. When the matter is target, we have restricted ourselves to the reflective properties in the optical remote sensing range. So we learnt about specular and diffuse reflectors. We also learnt about Rayleigh criteria for rough surfaces. And while discussing the interaction with the atmosphere, we've discussed the manifestation of absorption and scattering by the atmosphere on the remote sensing image. Now, with this, I'll stop here, and now I open this class for discussion. We'll have a 5 minutes break, and I'll collect your questions and we'll discuss. Thank you.